Good morning, America, and welcome to Diploma Review Unit 2. We're starting things off hot today. The first question is actually not a Unit 2 question. Right after I said we're going to do Unit 2, it's like, here's not Unit 2. So, the first question is one of these puzzles. So, we'll get these puzzles on your final exam / diploma exam. You are expected to take a significant amount of time, or you're at least budgeted a significant amount of time for these puzzles. So I want you to try it right now. If it takes you 5-10 minutes, that's okay. Stick with it and you can get these puzzles. The trick is always to try to figure out what the rules are and then try to complete the game or the puzzle. So go ahead, pause the video, try your best, and then unpause and listen to the explanation. All right. First things first with these questions. Always read the rules. So it says, the goal of a particular puzzle is to fill the circles in the grid. Fill the circles with letters A, B, C, D, so that no letters repeat in any row, column, or set of connected circles. So if you've ever played a game called Sudoku, it's kind of like that, where you're trying to put numbers into boxes and you can't have the same number in the same row. It then says, the 3 entries in the gray circles were given. So we know these 3 are good. They were given to us. Jerome has completed 3 entries shown in the white circles. So Jerome did the white circles, but he has made an error. Identify the error. To do this, I actually am not going to try to figure out what Jerome did wrong. Instead, I'm just going to ignore what Jerome put. I'll erase those after. And I'm going to just try to do this puzzle myself and then check to see which one of Jerome's answers is wrong. If I want to do this myself, there should always be some sort of process of elimination. So for instance, like try to find, in this case, we're talking about rows, right? Try to find a row that has 2 or 3 letters already given. So for instance, like this row has none given, this row has 1, this row has 1, this row has 1. None of my rows have more than 1 given. Now I'm going to try to check my column, see if any column has more than 1 given. This one has not 1, this one has 1, this one has 1, this one has no letters given, so that won't work. The next thing I want to do is check my connected dots to see if any of my connected dots have more than 1 given. These connected dots don't have any given. These connected dots don't have any given. These connected dots don't only have 1 given. But these connected dots have 2 given. So because of that, it kind of tells me that that's probably the easiest place to start is with these 4 connected dots. 1, 2, 3, 4. These 4 connected dots. Since I can't repeat any letters when I have connected dots, that means this either has to be A or B, or this has to be A or B. To tell which one is right, I then look and realize that this row already has an A. Therefore, this cannot be A, meaning that I can now make that B. And I know that I'm 100% correct on that. If that's B, then this must be A, because that's the only way I'm going to have all 4 letters in that connected row. Cool. Now I'm going to move on to another connection of 3, or at least 2. If I look at this row right here, I know that I have 2 letters already given, so I can fill in this spot or this spot. And the letters missing would be C and D, or C or D. And again, I notice this D in this column, meaning that that cannot be D. Therefore, this must be a C. Since that's a C, this must be a D. And you can see how this game works. You just continually keep narrowing yourself down, right? I've now filled in 2 of the blanks that Jerome had. If I check, I notice that he has made. Oh, has he made 2 errors, or have I made an error? Oh, I put a B here. Oh my goodness, Mr. Kennedy. That's a brutal way to start the video. My apologies. If we go back here, this should have been a C. I wrote B. That's brutal. I apologize. Which means that in these options, this would have been a B, and this would have been a D still. My apologies. Same logic and everything. I just wrote the wrong letter. Now I can check and see what Jerome wrote. I had a C here. He had a C there. That's good. I had a B there. He had a B there. That's good. That means this is likely his mistake right here. If we want to prove that that's a mistake, we need to continue on with the question. So ignore what he did, and let's continue on with the question. If I want to continue on with the question, the next spot that I see that's kind of obvious to me is that I need to fill in up here. I know that this column already has 3, so if I want to figure out the 4th one, this has to be a D up here. Awesome. If I want to keep going, I need to realize that I have a bunch of blanks here. This might be a good spot to focus on. Okay, so we could focus on that. Those 2 blanks have to be a B or a C. So B or C, B or C. However, because I know that these 4 connected dots right here are A, B, and D, that means this last spot has to be C. If that's C, that means this must be B, which is a mistake on their part. It should have been a C here and a B there. And I got that by using these 4 connected dots to get my C. Awesome. So his mistake was this one right here. Those games will and I said they could give you a gajillion different types of games or brain teasers or puzzles. Just take your time and really stick to them. Don't give up. That's honestly the biggest key. Find the rules and then don't give up. All right, let's get into actual Unit 2. So Unit 2 is called Perms and Comms. The first thing we did in Perms and Comms was we did these pathway problems. This question says, how many ways can George get from the bus station to the concert? So you have to walk from the bus station, walk to the concert. The way we did these is we looked at it and we asked ourselves, we pretended like all these corners were street corners, right? Like these are all little street corners. And we asked ourselves, how many ways could I walk from the bus station to this street corner? And the answer would be 1. There's only one way I could walk over there, right? And now that I'm at that street corner, how many ways could I walk to this street corner? And the answer would be 1. And then right across, that would be 1 as well. If I go back to the bus station, I also could have gone straight down, and there's 1 way I could have done that. 1 way I could have done that. 1 way I could have done that, and 1 way I could have done that. And that's kind of how the question always starts, with just 1s coming off of your starting point. You then have all these corners in the middle. So if we look at that red one I just did, the number of ways I could get to that red dot, I could come from above or from the left. That's 1 way from above, 1 way from the left, 1 plus 1 equals 2. That means there's 2 ways I could walk to this corner. If I look at my next spot right here, the number of ways I could get to that green dot, well, I could come from above, from that red dot, which is 2 ways, or I could come from the left corner, which had 1 way, for a total of 3 ways to get to that spot. And you're going to do this for every single corner. So 3 plus 1 is 4. 4 plus 1 is 5. And you're going to continue to fill this in all the way over. So this corner would be 2 plus 1 is 3. This corner, 3 plus 3 is 6. This corner, 6 plus 4 is 10. And I think you're getting the point, so I'm going to go a little quicker. This one would be 15. This one up here would be 4. This one would be 10. This one would be 10. This one would be, whoa. Man, it's late, I'm tired. This one would be 20. And this one would be 35. So there's 35 ways to get to this spot right here. But then we get into a little bit of a predicament. Because now it's like, where do I go? So the next corner I could walk to is right here. And the only way I could get to that corner is if I came from that 35. That means that there's also 35 ways to get to that blue dot. And the same thing if I went over one more. The only way I get to this spot is if I came from that 35 to the left. So the same way we started the question with ones, we now are doing 35s to fill in the side of my square. Same thing if I went straight down after I was at that 35. That means there'd be 35 ways there. If I went straight down, there'd be 35 ways there. But the other corners have 2 ways to get to them, so you have to add those 2 ways together. 35 plus 35 is 70. 70 plus 35 is 105. 35 plus 70 is 105. And last but not least, 105 plus 105 is 210. The number of different pathways he could take from the bus station to the concert hall is 210. Awesome. I want you to try this question on your own. Make sure you start at A and go towards B. So you're going that way. Pause the video, give it a shot. Wonderful. Hopefully you did that. To start this question off, I would go straight up. There'd be one way there, and straight up one way there. I'd then go left for 1, 1, and 1 as I walk across to these corners. The middle is going to be me adding. So 1 plus 1 would give me 2 ways to that corner. 2 plus 1 would be 3 ways to that corner. And so on and so forth. 2 and 1 is 3. 3 and 3 is 6. 1 and 3 is 4. 6 and 4 is 10. So there's 10 ways to that corner right there, which I'm going to do in purple so it stands out. 10 ways to that corner. That means if I went straight up to this corner, there's also 10 ways. And if I went straight up to this corner, there'd also be 10 ways. And so on and so forth across the left side. The middle numbers, if we were to fill them in, 10 plus 10 is 20. 20 plus 10 is 30. 10 plus 20 is 30. 30 plus 30 is 60. If I went straight up or straight left, those would both be 60. 60 plus 60 gives me a total of 120 ways I could get from A to B. Those are called pathway problems. I guarantee you'll have one on your final exam because I like those questions and they're always on the diploma exam if you write the diploma. Cool. Those are called grid pathway problems. We do get other pathway problems like this, which I call non-grid pathway problems, which are a little strange, a little different. The way these pathway problems work is you start in a town. This one is started in Winnipeg trying to get to Saskatoon. So I started here at Winnipeg trying to figure out how many routes could I get to Saskatoon. To do that trip, you're going to have a hub city. So when you leave Winnipeg, you'll notice there's 3 different routes, but all 3 routes go to Regina. right? There's one that goes up, there's one that goes through the middle, and there's one that goes straight down. But in total, there's 3 different ways that you could get from Winnipeg to Regina. Once you're in Regina, you have 2 different pathways that you could use to get to Saskatoon. For non-gridway problems like this, where it's kind of crazy and you have these hub cities, what you want to do is multiply your numbers together. So there's 3 ways that you can get from Winnipeg to Regina, and then you're going to multiply the 2 ways it takes to get from Regina to Saskatoon. This will tell you the total number of ways to get from Winnipeg to Saskatoon, and it's 6. Awesome. Those are pathway problems. We're going to get into a little bit more of the mathy stuff now for Unit 2. We're going to talk about factorials. So factorials was something we learned. A factorial looks like this. So factorial is like 4 and then an exclamation mark. What that exclamation mark means is that you take the number in front of the exclamation mark, so 4, and then you're going to multiply it by every number less than it. So multiply by 3, multiply by 2, multiply by 1. Those 2 things mean the same thing. If you were to calculate them, they both equal 24. The factorial button is in your calculator. If you hit math and then hit over to the right 3 times, you'll see number 4 is your exclamation mark. The reason we use this is to help us count like situations to things. So for instance, example number 4 we got down here, it says if 30 grade 2 students need to stand in a straight line before leaving class, how many ways could they stand in line? The way we would do this is by using something called the fundamental counting principle, FCP. Anytime you're arranging something into a nice neat line or sitting them in chairs or something like that, you could draw placeholders. In this case, there's 30 grade 2 students, so that means there's 30 placeholders. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 25, 26, 27, 28, 29, 30. Holy Toledos, that's a lot of children. Okay, then, so these lines represent the 30 different spots in line that a kid could sit. In the very first spot, you ask yourself how many kids could stand in the first spot in line. And the answer would be 30, right? There's 30 different kids who could sit there. In the second spot in line, now how many kids are left that could sit in that second spot? And the answer is not 30 because one of the kids is in the first spot. Now there's 29 kids left. The next spot would be 28 kids, and so on and so forth. We're going to go down the line until we get down to 4 kids left, 3 kids left, 2 kids left, 1 kid left. The reason we do this is because these numbers are actually giving us a calculation to make. In between these numbers in the fundamental counting principle are little multiplication symbols. So this is really 30 times 29 times 28 all the way down to 1, which means our answer is 30 factorial. There's 30 factorial ways that these kids could sit in a line or stand in line. If you tried to actually calculate 30 factorial, you'll notice your calculator says the letter E. That means the number is too big to even calculate. So 30 factorial would be our final answer. Cool. That's Introduction to Fundamental Counting Principle. We're going to do a few questions with it now. So we'll rearrange some letters and words. So this says, how many ways can the letters from the word hockey be arranged? The first thing you want to do is figure out how many things you're arranging. In this case, there's 6 letters. Since there's 6 letters, that means we have 6 spots. In the first spot, how many different letters could I put? Well, if there's 6 different letters, that means I could choose any of the 6 to go in the first spot. In the second spot, though, I've taken away one of the letters. That means there's now only 5 things that could go in the second spot when I'm arranging these letters. In the third spot, there would now only be 4 letters to choose from, and then 3 letters to choose from, then 2, and then 1. Remember that we are multiplying all of these letters together. This is the same thing as saying 6 factorial. If you put 6 factorial in your calculator, or you go 6 times 5 times 4 times 3 times 2 times 1, you can do it whichever way you want. You should get that there's 720 different ways that you could arrange the letters in the word hockey. If you want to pause and try number 6, you can do that. For number 6, the number of letters in uncopyrightable is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different letters. 15 different letters. That means there's 15 spots that I can put these letters in when I'm arranging them. Fun fact, uncopyrightable is the longest word in the English language with no letters the same. Okay, in the first spot, when I'm arranging these letters, there would be 15 different letters to choose from. I could pick any of those letters, but once it's picked, it's gone. That means in the second spot, there would only be 14 letters left. And now I've picked 2 letters, so they're gone. That means there's only 13 left, and 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. A reminder that using fundamental counting principle, these numbers are all being multiplied together. When you multiply them all together, that creates something called 15 factorial. That would likely be your answer on a test, 15 factorial. If you put 15 factorial on your calculator, you get the letter E, which doesn't work. So the answer is just 15 factorial. Wonderful. Number 7, Mr. Kennedy needs to make a seating plan for 25 students in his class. How many seating plans could he create? All right, but we don't even know what my seating plan looks like. I don't know if it's a straight line. I don't know if it's 10 rows. I don't know. All that matters is that you have 25 seats. Okay, it doesn't matter what they look like. It doesn't matter if it's a big circle. It doesn't matter. But you have 25 different desks. And in that first desk, I have 25 different names to pick from. Once that student's gone, I now have 24 to pick from, 23, 22, 21, and so on and so forth until I've picked every student. My answer would be 25 factorial. There's 25 factorial ways I could sit those kids. Cool. That is like basic fundamental counting principle. We then have all different types of situations that happen. We have repetitions, we have rules, we have groupings. It gets much harder than that. So that's like the basic fundamental counting principle. We'll do we'll do repetitions and then we'll probably stop there. We'll do repetitions and then we'll do one set of restrictions. Some words or things, when you're arranging them, have repetitions. So, for instance, when they say, how many ways can you arrange the letters in the word Kennedy? You notice that there's some repetitions in letters. There's 2 N's, 2 E's. And that is going to affect how we have to do the question. But we start at the exact same. So I'm going to count how many letters there are. There's 7 letters. That means there's 7 spots to sort these out. In the first spot, I could pick any of the 7 letters. In the second spot, I'd be left with 6, then 5, then 4, then 3, then 2, and then 1, giving me a total of 7 factorial ways that I could sort those letters. Unfortunately, that is not the correct answer, though. The reason it's not the correct answer is because if I wrote out the word Kennedy, let's write it out, Kennedy. And if I took those letters, imagine they're like letters I can move around. And I took those two ends. I took the red end and the green end, and I switched them spots. The word that I would spell out if I switched those end spots would still be Kennedy. The word has not changed. That's because those letters are the exact same. That's called a repetition. And what happened is in this 7 factorial, we're saying that these two things are different when they're actually not different. Right? Those are the exact same words. They're both Kennedy. So we have to somehow deal with those repetitions. The way we deal with those repetitions is we divide repetitions. That is one of our big rules. So when I have my answer of 7 factorial, I then have to divide by repetitions. In this case, I have 2 n's, so I need to divide by 2 factorial for the n's. I also have 2 e's in the name Kennedy, so I need to divide by 2 factorial again for the e's. So my correct answer is 7 factorial divided by 2 factorial times 2 factorial. If you were to put this into your calculator, you would get 1,260 ways that you could sort the word Kennedy. Cool. We also see repetitions in different types of word problems like this one below. It says Frank has 10 fruit that he wants to arrange in a line. He has 3 bananas, 2 apples, 2 oranges, 1 pineapple, 1 watermelon, and 1 cantaloupe. How many ways can he arrange the fruit? Well, if we think about this, I'm just going to write them out using letters. He has 3 bananas, so B, B, B. He has 2 apples, A, A. He has 2 oranges, 2 O's, a pineapple, a watermelon, and a cantaloupe, the lowest of the fruits. He wants to sort those fruit. Well, that's the same thing as saying, how many ways could I sort those letters I just wrote out? If I look, there's 10 letters here. That means there's 10 different spots that I could sort these fruit. And in the first spot, I could put any of those 10. In the second spot, I would have 9 fruit to choose from. Then 8 fruit, then 7, then 6, then 5, then 4, then 3, then 2, and then 1. For a total of 10 factorial ways that I could sort those fruit. However, within these fruits, we have repetitions. Right? There's 3 bananas. If I take those bananas and I switch them spots, it still goes banana, banana. So I need to divide repetitions. I need to divide by 3 factorial for the bananas. I need to divide by 2 factorial for the apples. I need to divide by another 2 factorial for the oranges. The correct answer is 10 factorial divided by 3 factorial, 2 factorial, 2 factorial. If I put that in my calculator, you end up getting 151,200 ways in which you could sort those fruit. Ta-da! That's how we deal with repetitions. We actually are going to stop right there. We'll do restrictions. We'll start that tomorrow. This is a good place to stop. So if you want to go into your key booklet and try to do the basic fundamental counting principle, that's very good use of your time because tomorrow fundamental counting principle is going to get a lot harder. So make sure you go and you practice today all the easy stuff, the basic fundamental counting principle. Awesome. Take care. Pop into the chat if you wanted to ask any questions or need help. See you soon.